Hey everybody! So today we are diving into a really massive engineering puzzle. How in the world do you safely and permanently store captured carbon dioxide deep underground? It's a technology that could be a huge deal for our climate future, and really, it all hinges on one very special, very sophisticated piece of tech, the CO2 injection well.
So let's just start with the biggest question right out of the gate. It sounds simple enough, but how do you actually bury a gas and then be completely 100% sure it's going to stay there? Not just for a few years, but for thousands of years. Forever. That's the challenge we're going to unpack.
Now, you might be thinking, isn't a CO2 well just an oil well running in reverse? And yeah, they can look pretty similar from the surface, but their jobs and the challenges they face, they are worlds apart. One is all about getting something out of the ground. The other is designed for permanent containment. And trust me, that one word, permanent, changes absolutely everything.
Okay, let's get into it. Before you can understand the solution, you really have to appreciate the problem. And as it turns out, CO2 is a surprisingly tricky customer to deal with when you're trying to lock it away for good.
See, if you want to build a well that lasts for eternity, you're not just fighting one thing. You're fighting three distinct threats all at once: a chemical attack, incredible physical pressure, and wild temperature swings. Let's break each of those down. So, problem number one is corrosion. When CO2 mixes with water, and there's almost always water deep underground, it creates something called carbonic acid. Now, it's a pretty weak acid, sure, but over hundreds and thousands of years, it can chew through standard steel and cement. It's like a slow-motion, relentless rust. The second hurdle? Just immense pressure. To store CO2 efficiently, you can't just pump it down there as a regular gas. You have to compress it so much that it becomes this dense, almost liquid-like fluid. And doing that requires incredible injection pressures that the entire well has to withstand, 24/7. And third, here's the one you might not see coming: the temperature. That super compressed CO2 we're injecting is often really, really cold. And what happens when metal gets cold? It shrinks. That contraction puts a ton of stress on all the well's components and can threaten the seals if you don't plan for it. So you've got corrosive acid, crushing pressure, and thermal stress. That is a tough combo. But for every one of these challenges, engineers have come up with a very specific solution. It's time to look at the specialists' toolkit they use to build these incredible wells. This strategy is basically a direct counterattack. First, you design the entire structure to handle those massive forces. Then, you choose every single material to be basically immune to that carbonic acid. And finally, you engineer the whole system so it can handle those temperature swings without breaking a sweat. And let's be clear, we are not talking about parts you can just pick up off the shelf. This is a highly specialized shopping list for some of the most extreme conditions imaginable. We're talking advanced metal alloys that laugh at corrosion, special cement recipes that are completely different from the stuff in sidewalks, and materials chosen specifically to handle that intense cold. Out of all those specialized parts, there is one that is arguably the most important for making sure forever really means forever, and that is the seal. It's the cement that creates the ultimate lock, guaranteeing that what goes down stays down. You know, the engineering documents put it perfectly. They say the cement sheath plays a crucial role. That's an understatement. It's not just some filler. It is the final barrier that keeps the well intact and completely isolates the CO2 deep in the earth. And this part is absolutely non-negotiable. If you tried to use standard everyday cement, that carbonic acid we talked about would just eat it away over time. That could create tiny pathways for leaks. Only this specialized CO2-resistant cement can give you the permanent seal you need. So, why all this painstaking, incredibly expensive engineering? Because the stakes couldn't be higher. This isn't just some industrial project. It's an environmental promise for the long haul, and it is governed by a very, very strict rulebook. In the US, these wells have their own special designation. They're called Class V wells. And this isn't some optional guideline. It's a whole regulatory class from the EPA, loaded with requirements designed for one thing: long-term, safe CO2 storage. And the number one priority, the main goal of all these regulations, is something that matters to every single one of us: protecting our sources of drinking water. That's what it all comes down to. All of this complex engineering, the special alloys, the fancy cement, the pressure management, it's all there to make sure that CO2 stays locked deep underground and our water stays safe for generations.
So, if there's one thing to take away from all this, it's that a CO2 injection well is not just a pipe in the ground. It's a highly sophisticated, multi-layered containment system engineered from top to bottom with one single-minded goal: permanence. This kind of incredibly detailed engineering is a really critical piece of the whole climate puzzle. It kind of makes you wonder, doesn't it? What other hidden innovations, these complex but totally essential technologies, are we going to need to invent and perfect to build the future we want?